Hello and welcome to the review for Unit 2 of Algebra 1B. In this unit, we have been talking about exponential and radical functions, and there are a lot of really practical purposes for the use of these types of functions, but they require a pretty good foundational skill. I know this isn't new for most of you, but we did make our equations and our expressions a little bit complex, so it's a good idea to have some of these things in your notes before you start your unit tests. Some of the things that we learned about are simplifying exponential expressions, graphing those exponential functions, working with scientific notation, simplifying radicals by adding, subtracting, multiplying, and dividing, graphing radical functions, and solving radical equations. Now, some of the properties of exponents you're probably already familiar with. First, just the basic idea of what an exponent is. Remember, a number raised to an exponent means that you will be multiplying that number as a factor the number of times of the exponent. The most common mistake is for somebody to multiply the two numbers, like think that 3 squared is 6 instead of 9. So remember, the little number has nothing to do with multiplying by it. It's just the number of times you'll multiply the base as a factor. In this case, 7 to the 5th power will multiply 7 times 7 times 7 times 7, and that will be 823,543. These numbers get very big very fast, and that's why when we talk about exponential growth, we're talking about something that happens very fast. One special case about exponents that doesn't always make logical sense is that 7, if it's raised to the power of 0, is equal to 1. And that's the case for any base that is raised to the 0 power. It could be 0 to the 0, it could be 1,000,000 to the 0. It would still equal 1. Remember, a power raised to another power is, there's a little shortcut. You can multiply these two powers together. So if I were to simplify this whole expression, the b, instead of being to the 4 and then again squared, it would be raised to the 8th. And that makes sense because if it's squared, that means I'm going to multiply b to the 4th twice. And if I multiply 4 factors of b times 4 more factors of b, I would have 8 in all. Now here, this is a little bit more complex. X is raised to the 4th, but outside the parentheses is a 3. So I'm going to follow that same rule and multiply the 4 times the 3 for the x only. Then I'm going to go back and grab that y. It doesn't have a beginning exponent, so it's only going to be raised to the 3rd power outside those parentheses. So this becomes y to the 3rd. So this is the simplified way that you would write that expression. Now, when you are working with adding, subtracting, and you're doing several of them in an equation or an expression, it's easy to start thinking and getting into the habit of using the shortcuts, and that's what I'm going to show you about here. Y to the 4th power times y to the 3rd power will become y to the 7th power. Why? Because the rule is if the bases are the same, I can add the exponents. Now, why does that work? Well, again, I've got 4 factors of y being multiplied together, and I'm going to multiply them by 3 more factors of y, so that's going to be 7 in all. The same thing is true when you're dividing exponents. Y to the 7th divided by y to the 4th is going to be y to the 7th minus 4, or y to the 3rd power. So when you're dividing and the bases are the same, you get to subtract the exponents. If you're multiplying and the bases are the same, you get to add the exponents. If the power is raised to another power, you get to multiply those. Now, these rules aren't so hard once you get used to using them, but while you're getting used to using them, make sure that you've got them in your note. Here's an example of something you should be able to solve with just the information that we just talked about. When your expressions are fairly complex, don't let that scare you. Just take them apart piece by piece, looking at just the numbers first. And here it doesn't appear that there's a number in the second factor, but remember, a minus sign in front of something means it's being multiplied by -1. So 6 times -1 is -6, and the numbers are done. Now I'm going to the a's. I have one factor of a and one more factor of a, so multiplied together they become a squared. I have 3 factors of b that I want to multiply by one more factor of b. That means that b will have a total of 4 factors, so it's raised to the 4th power. The c in the first factor is single, but it's being multiplied by 2 more factors of c for a total of 3 factors of c. Sometimes you will see fractions as an exponent, and this is something you may not have seen before. A fractional exponent means that you are taking a root of the number that's in the base. That means if the number is 2 in the denominator of the fraction, you'll be taking the square root. If it's a 3, you're taking the cubed root. If it's a 4 or more, you're taking that root. And another way to write it, sometimes you'll see a little number right here in the crook of the square root sign that tells what the index is or what root you are taking. So in this case, 25 to the 1/2 is the same exact value as the square root of 25, which is the same value as 5. And on your calculator, if you were going to use this, you would hit the 2, then the 5, then the square root button, and it would give you the number 5. Another thing that you can do to try this out on your calculator, hit the 2 and the 5, hit the exponent, the x to the y button up here, and just put in 1/2 as the exponent. You can either change it to 0.5 or you can use the parentheses, open the parentheses, type 1 divided by 2, which is 1/2, close the parentheses and hit equal, and you should get 5. So try it out on your calculator and make sure that it works before you try to use it on a test. Okay, so 16 to the 3/4 is a little bit more complex, but it can be solved in many different ways. First of all, you can do the same technique on your calculator, putting in the 16, raising it to the 3/4 power, or you could change it to a decimal, which is 0.75. Or, since the 4 is on the bottom of this fractional exponent, it is going to be the root of this base once it's put into a square root sign. The 3, which appeared on the top of the fraction, is an exponent either to the base itself, or after you've taken the root, it can be raised to that exponent as well. Either one of these will have the same value, and you can test them out on your calculator and see. I just need to tell you that if you're using your built-in calculator on your Windows-based machine, you have to hit this second button before you can get to the place where you can take any root of a number. So it's in the same place as the x to the y button. It is the y root of x, and when you use it, you just put in your number 16, hit that multiple root button, then in this case you'd hit 4 because that's the root that you want, and then equal, and it will do the work for you. Now another variation on exponents is the negative exponent. A negative exponent means that you are going to be using the reciprocal of the base instead of the base itself. So always think of it as a fraction or something between 0 and 1, and put a 1 on the top of your fraction like I've done here. Take the same base and put it in the bottom of the fraction. Take the same exponent except in its positive form and put it on the base in the bottom of the fraction. So this would be simplified to 1 over, let's see, 5 times 5 is 25 times 5 is 125. So this would be the fraction 1 over 125. X to the, or 5 to the negative 3. Remember, you can always use your calculator to find a negative exponent, but it will give you the value in a decimal form. And sometimes in your multiple choice questions, you are asked for the fraction. So be sure that you can do it both ways. Now, evaluating an exponential expression simply means that they're going to give you some values for the exponents. You need to replace the variables with those numbers and then solve it using the order of operations. So in this first example, I have h to the negative 2g. Well, h is going to be 3 and g is going to be 27. So first I'm just going to rewrite it as 3 to the negative 2 times 27. Well, I recognize right away that 3 being a negative exponent is going to be a fraction. So I can rewrite that as 1 over 3 to the positive 2. 1 over 3 to the positive 2 is 1 over 9. And if I want to multiply that by 27, I can make the 27 into a fractional number by putting 1 underneath it. And then by multiplying straight across, I simply have 27 over 9, which is the same as 27 divided by 9, which is 3. Okay, what about this one? X to the 0 plus y to the 0 when x is 3 and y is 2. Now I could go ahead and replace these variables with the numbers, but it really isn't necessary since I know that whatever the numbers are, if they're raised to the 0 power, they will be 1. So this is 1 plus 1, or 2. All right, exponential functions are often used in cases of money being compounded, populations growing, decreasing, property increasing in value or decreasing in value. There are a lot of very practical ways to use exponential functions. Just make sure that you read the problems carefully and you understand which of these equations that you need to be using. The basic equation for money is a of t equals p times 1 plus r raised to the t. That is, the amount that you will have after a certain amount of time equals the principal, p, which is the initial investment, times 1 plus the rate that it's being increased by, and that will be raised to the time. So this usually applies only to annual interest rates. That's why I've underlined that. So let's see if we can get the numbers in the right place. The initial deposit is $50, so that's going to replace the P in the equation. I'm going to multiply that by 1 plus the rate. The rate is 5%, and I want to be able to write that as a decimal. So dividing it by 100 gives me 0.05. And I'm going to raise that to the t years. They don't tell us how many years it is. And this is going to equal the amount that I have in my account after t years. Okay? So according to the order of operations, I've got to take care of my parentheses first. 1.05 is 1.05. And then I'm going to multiply this by 50. Now notice that I can't do the multiplication until I apply the exponent. And since we don't have the value of the exponent, this will be your final answer when you are asked to answer this on your test. Okay, here's another investment problem from your test where a certain amount of money is invested at 7% compounded weekly, and you need to find the value of the investment after 5 years. Well, we're going to use a slightly changed equation. It's going to look very similar, but I'm going to change it out because if it's going to be compounded every week, that's going to be 52 times during the year. So again, I'll put my principal in where the P is, and I'm going to multiply that by 1 plus, and here's where it gets different. I still want the rate, in this case it's 0.07, but I'm going to divide that by 52 because there are 52 weeks in a year. Then I'm going to raise this whole thing to 52 times the number of years. In this case, it's 5. That is supposed to be 0.07. I'm not sure what I said when I wrote that, but that's Oh, I wrote 52. Yes, it's supposed to be 52 times 5. Sorry. And the reason why I'm making a mistake is this should be NT up on top. There we go. Okay, so N is the number of the weeks in a year, and that's why that's written up there. So the order that you would do this is you wanted to take care of the parentheses first. Inside the parentheses, there is a little division to be done. Throw this into your calculator, do 0.07 divided by 52, add it to 1, raise it to 52 times 5, then go back and multiply it by 9,250. Check to make sure that your answer is reasonable. It should be more than the initial rate money invested. Now, a relative growth rate for a certain type of bacteria, I underline the word population. Population is always considered to be compounding continuously. So if you have a bank problem that says compound continuously, or if you're talking about a population, you will be using this formula right here. P of t equals P times e to the RT. Now P again is not going to be an initial investment, it will be the original amount in the population. E is a constant that we use, and it's kind of like pi. It just has a value, but it never ends. It's an irrational number. But we use an approximation for it, and it is in your calculator, 0.18, I think that's a 3. But it's approximately 2.1783. So to set this up, we have to decide, is this the bacteria that we have now, or is this the initial amount? It says this is the amount that we have in 5 hours. So this number is going to go on the left side because it is the total we have now, and we're trying to find the initial amount. So the number we find will have to be smaller. I'm going to leave P in here because that's what we don't need. I'm going to replace the E with a 2.1783. And I'm going to raise that all to the RT. The rate is 78%. 78% divided by 100 can be used as the variable, and that's times 5 hours. So the first thing I would do here is multiply the 0.78 times 5. Then I would apply it as the exponent to 2.1783, or e if it's in your calculator. But at this point, you can't multiply it by anything. You need to go back and divide the 34,825 by whatever value you get when you raise e to the 0.78 times 5. Scientific notation is used for very large and very small numbers, and it allows you to make very complex calculations without having to fill up your calculator with a lot of numbers. Remember the rules of scientific notation. It has to contain a single number between 1 and 10. It has to be multiplied by a power of 10. If you're doing a multiple choice question, you've done all the work and figured out the answer, do not choose one that is not in the proper form, because that won't be the correct answer. It always has to have a number between 1 and 10. So for instance, let's write 7,001,095 in scientific notation. Every number has a decimal point. In this case, it comes right after the 5. In order to make this into a number between 1 and 10, I'm going to have to divide. And I'm going to divide by 1, 2, 3, 4, 5, 6 factors of 10 and put the decimal right after the 7. Then I can rewrite this as 7.001095. And because I ended up dividing by 6 factors of 10, I have to multiply by 6 factors of 10 in order to make this have the same value that it had before. So by moving the decimal point, I'm dividing. So my exponent is going to represent the multiplication by the same number of powers of 10 that I used. We had a section on geometric sequences, and you're going to be asked to do several different tasks with those. First of all, make sure that you know how to find the common ratio. The common ratio is found by taking any of the values in the sequence. I'm going to pick -2 and dividing it by the number to the left. In this case, I'm going to be dividing by 8. This equals -1/4 when reduced. When you get the common factor, make sure and just check it out. For instance, here, if I had -2 times -1/4, I really would get 0.5, and it would be positive because I'm dividing a negative by a negative. Now, for this one, you are supposed to find the recursive formula and the 6th term in the sequence. Well, this first one that I've written is the reclusive formula, and it just kind of represents the information from the sequence. It always contains 2 parts. First, the basic equation or formula, and then always what the first term is. We know that our first term here is 3, so we can rewrite this equation as a sub, let's say that we're looking for 4, equals the rate, and I didn't do the rate yet, so let's take our 6 and divide by 3, and that gives us the number 2 for our common ratio. So that equals 2 times the one that came before that, which was A3. Well, A3 is in this sequence 3, 6, 12, so that would be 12. If I multiply 2 times 12, I get 24. So A sub 4 is 24. If I continued on to A5, I would just write 2 times 24, because that was the A to the 4th, and that would equal 48. And you'd have to do it one more time to get to that 6th term in the sequence using the recursive formula. Remember the 2 parts. There's the formula itself with the rate and the first term, and the second part where it says where A1 is 3. Now, let's say that this was asking you for the 60th term instead of the 6th term, and you needed an equation that you could use instead of just going one by one with the recursive formula. Well, you can still write it using this second formula that I've listed here. And this is A sub, let's say it's 60, equals the first term in the sequence, that's A1, is 3, times the rate, which was 2. And this time we're going to use an exponent, and it's going to be 1 less than the number we're looking for. So it's going to be raised to the 59th power. Now I'm not going to do this work for you, but you'd raise the 2 to the 59th power, go back and multiply by 3, and that would be a very, very big number. Simplifying radicals. Is this number 1.69 rational or irrational? You're asked that question in your test. Well, the only way to find out is to take the square root of 1.69. If it comes out without an decimal that goes on forever, then it is rational. In fact, I happen to know that the square root of 1.69 is 1.3. So this is a rational number. And that's the thing that you need to focus on when you're working with radicals. Can you simplify it so that it's more useful to us? Because when things are in the square root bracket, they become cumbersome to work with. So let's say you were asked to simplify -3 times the square root of 84x cubed. I want to take this -3 and leave it alone for a while. And I'm going to start breaking up this 84x cubed so that possibly I can take some of the factors out. When I do this, I'm always asking myself, what is a perfect square factor of 84? Well, you might have to do what I do and just list all the perfect squares so you can kind of test to see which ones are factors of this particular number. So 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, and I think that's about as high as I need to go. Any of these look like they might go equally into 84. I know that 4 goes into it 21 times. So I'm going to split it up into 4 times 21. So 4 times 21. And then I'm also going to split up my x's because I happen to know that if x or any variable has an even number as an exponent, I can take the square root of it. If it has an odd one, then there's going to be one left over that I won't be able to simplify. Now remember, you can break this up into the square root of 4 times the square root of 21 times the square root of x squared times the square root of x. And the reason I did that is because I know that the square root of 4 is 2. So I don't need that anymore. The square root of 21, however, is simply square root 21. The square root of x squared is x, so it can come out of the bracket. And then I have one remaining x inside the bracket. So to multiply all of these things together, I'm going to multiply -3 times 2 to get -6. And I'm going to multiply, 6, and then this x will go with it. Now the two things that are inside the radical, the 21 and the x, can also be multiplied, but they have to stay inside that bracket, 21x. Okay, another rule about simplifying radicals is that if you have a radical sign in the denominator of a fraction, you have to get rid of it. It's just not allowed. So if you are given a square root that has a fraction inside, remember that you can break it up so that the top and the bottom have separate square root signs. This is going to come in handy because we won't have to do quite as much work. Now the square root of 7 can't be simplified, but the square root of 12 I know happens to equal the square root of 4 times 3. And the reason I chose 4 is because it's on my perfect square list. And if I take the square root of 4, I end up with 2. And the square root of 3 has to stay inside the square root. Now, let's get ourselves some more space over here. Right now we've got square root 7 on top. And on the bottom we've got 2 times the square root of 3. Now, in order to get rid of that square root 3 on the bottom, I have to multiply by the square root of 3, because multiplying a square root by itself will undo the square root. I have to multiply the top by the same value, or it won't have the same value in the end. The square root of 7 times the square root of 3 is the square root of 21. The square root of 3 times the square root of 3, however, is just 3, and 2 times 3 is 6. So this would be the simplified way to write the square root of 7/12. Now take a look at these next terms. Do these have the same value? Well, we talked previously about fractional exponents, so you might be able to calculate these on your calculator, and that is what I would recommend that you do. We've got this simple number 256, then we've got 1296 to the 3/4 power. Well, I happen to know that the 3/4 means there will be a fourth root and an exponent of 3. So I'm looking over here at the fourth root of 1296 raised to the 3rd power, and I know, because of what I know about fraction exponents, that these two are equivalent. So if I had to pick that which ones of these were equivalent, I would pick those last two. However, I think that they will equal 256. You would have to do the work on your calculator to see if they match. And this particular question on your test has several questions that are like this, where you have to choose which ones have a different value. All right, multiplying and dividing radicals. Multiplying is pretty easy. You just multiply the number portions as we did before. -1/8 times 1/2 is -4. Then when you multiply the radical forms, you can multiply the numbers that are inside them. This case, 32 times 2 is 64. which is really nice because the square root of 64 is 8. So this is 8 times -4. And together they make -32. All right, what about this one down here on the bottom? It looks pretty nasty. Well, I'm looking and I think I can actually divide every single term by 2. I'll do that first. 8 divided by 2 is 4. 6 divided by 2 is 3. And 2 divided by 2 is 1. Now I'm going to be able to rewrite this slightly. So I've got 4 times the square root of 6mn, and I'm going to rewrite it a little differently because I want to split it up into 2 different fractions. And when they put one denominator below it, it just means that I'll have to use it underneath each half. And then I'm going to add this, and I change this to 3 times the square root of 8mn over 2mn. And I'll show you why I chose to do it this way. I happen to know that if you have a fraction, if you have a radical on the top and the bottom, you can combine those into 1. So this would be 4 times the square root of 6mn, 6mn over 2mn. And this one will be 3 times the combined 8mn over 2mn. Okay, in the 6mn inside this radical, the m's cancel out in the top and the bottom, and the 6 over 2 turns into 3. So this becomes 4 square root 3. Over here inside the radical, I'm going to divide 8 by 2 and get 4, but the m's and n's both disappear. The square root of 4 is 2, and I multiply that by the 3 that I already have, and I get 6. So simplified, this would equal 4 root 3 plus 6. All right. When you're adding and subtracting radicals, you're always trying to get them to match. If you can get radicals to match, then you can treat them just like variables and add the coefficients. So first of all, we're going to be doing some simplifying, then we're going to be adding and subtracting. From this one, I know that I can break this up into 9 times a squared. The square root of 9 is 3, and the square root of a squared is a. So I don't need that radical sign anymore. I can break up this into 49 and b. I happen to know that the square root of 49 is 7, and there is no more simplification for the square root of b. Minus a plus square root b. So to combine like terms, I do have another a term, so I've got 3a and minus 1a for a total of 2a. And I've got 7 square roots of b plus 1 more square root of b, and I can combine those because they have the exact same square root. So that's going to be plus 8 square root b. And that is the simplified form of this expression. Here's another one that looks like you probably won't be able to add these together. But let's take a look at how we can rewrite square root 8. This can be square root 4 times 2, and this could be square root 25 times 2. Okay, so this will equal the square root of 4 times the square root of 2. And the square root of 4 is 2, so this is 2 square root 2. And now I have 25 times 2 inside, So that equals the square root of 25 times the square root of 2. The square root of 25 is 5, so this is 5 square root 2. Now all of a sudden I see that in my little tiny equation I have the square root of 2 in both of the terms, so I can combine these terms by just adding the coefficients. And this will become 7 square root 2. All right, in radical functions, that means that you're going to have a radical on one side of your equation, and depending on what's included in the radical sign, you probably need to get that radical isolated on one side of the equation, then square both sides in order to be able to solve it. So in this example, they want me to solve for x. I don't want to, normally in this unit, you've been trying to get the radical all by itself, but in this case it says don't solve for what's in the radical, solve for x. So I have to get rid of everything on the left side of the equation. So I'm going to start by just getting rid of this 1. And then I'm going to have x over 2 equals square root 3 minus 1. Then my last step is to multiply both sides by 2. That will cancel the 2 on the left and give me a 2 square root 3. And then I guess I could change this to minus 2. So the answer to this is 2 root 3 minus 1. Wait, I multiplied, so times 2. There we go. What about this other one? It says 1 over 5 to the x equals 5 to the 8th. Well, let's see what I can do. Because I know that a fraction is made when an exponent is negative, if I want to get rid of the fraction, I can flip this upside down and write it as 5 to the negative x. And if that equals 5 to the 8th, then I know that this minus x exponent has to equal this 8 exponent in order for them to be equal. So if minus x equals 8, I know that x can be found by multiplying both sides by negative 1, and x will equal negative 8. All right, we also had some practice graphing. Now I really recommend that you use Desmos.com for your graphing. Some of these are very complex and difficult to sketch on your own. However, if you're used to using graphs on your own and you want to submit them that way, then that's fine. I think you have 2 or 3 graphs on this test that you'll need to submit. Now I told you before that sometimes it just depends on how the problem is set up, but usually if you have a radical in your equation, you want to isolate that part, and then you'll be able to square both sides and solve. Now the question is, what is the root? That means what is the value for the variable? And if it has no root, choose none. Well, how could it have no root? Well, if you graph this equation and it doesn't cross the x-axis at any particular point, then it doesn't have a root. But you can also test when you find the value of z. You can go back in and test it and see if it works out. So what I'm going to do here is, I think, subtract 4 from both sides of this equation. And that will give me 3 minus square root 3z plus 2 equals 0. And then I'm going to add this whole radical term to both sides. So I'm going to get 3 equals square root 3z plus 2. Now the reason I chose to do it that way is because I wanted to get this radical all by itself so that I can square both sides. In this case, squaring the number on the left, 3 squared will give me 9. And squaring a square root just undoes the square root, so that leaves me with 3z plus 2. Now I can solve this like a regular algebraic equation by subtracting 2 from both sides. That gives me 7 equals 3z. And by dividing everything by 3, I can find the value of z. Okay, so z equals 7/3. Now they want me to go back in and use 7/3 and make sure that it works as a solution. I'm not going to take the time to do that, but if I did so, I would multiply it by 3. I would add that to 2, take the square root of it, and if 7 minus that, well, I'll go ahead and do it since I've already talked you through it. So if I have 7 minus the square root of 3 times 7/3, I happen to know that 3 times 7/3 is 7 plus 2. Inside the radical, I've got 7 plus 2, which is 9. The square root of 9 is 3. So now my equation is 7 minus 3 equals 4, and that is true. The times when you find that there is no root is when you have a negative number or possibility of a negative number inside a radical. And remember that you can't have a negative value inside a square root sign. Now, these two you are just asked to graph. And you might be asked for the domain, you might be asked for the range, or you might be able to predict as x increases what's going to happen to the function. So I've actually graphed this one for you. This is the top graph up here. And you can see that because there is a negative in front of the base, that this flipped over into the quadrant, well, the lower half of the graph. But you can see that it is never actually approaching 0 as it goes this way, but it is getting infinitely more as it goes this way. So you should be able to describe a graph, and this is a typical graph of an exponential function. Now, you've had several of this next type of problem in your lessons, so you should be familiar with them. You'll have one for square roots of x and cubed roots of x. They'll give you a series of numbers that you need to use for x. You need to plug those into your calculator and find the corresponding points on the graph. Now I've done one for you, and this is in Desmos. I simply put in the points. So for instance, I know that when 0 is the exponent for negative, or for when 0 is put in as the square root, the point I'm going to get is 0, 0, because 0's square root is 0. The next one will be 1.44, and if I take the square root of that, I believe I get 1.2. So you'll start picking up these points, put them in a chart in your answer area, and then graph them in Desmos. Remember, it will not be a line or a curve, it will be these individual points. Okay, that brings me to the end of our review. I realize this one was kind of long, but we did cover a lot in this unit. If there was something that you were concerned about that I didn't cover or didn't give you enough examples, please let me know, and we can definitely talk about that before you take the test. Remember that you're required to give me a call, so when you do, just kind of look over your other grades in this unit, make sure that you're happy with what you see. And again, if you've got all these things in your notes, you should do really well. If you have any remaining questions, please tell me at that time, and we'll take care of them before you take the test. Thanks for coming in.